Good morning. Put that down. So my commute here would have been a lot easier in Bloodhound supersonic car. It's a fantastic project. I've been on it now for 10 years. My background is defense aerospace. So I worked on projects. I was working on the X-32 for Boeing. I spent 2 years in Seattle. I was then part of the team that took the F-35 to flight test and did the STOVL version of that aircraft. Now, we're talking about technology and how things change and what you use. So 10 years ago, I got home from work one day, and those little lights used to flash on a thing called an answering machine when you didn't used to have a mobile phone that you relied on. And there was a message left on it, and it said to me, a mutual acquaintance has suggested that you would be somebody that might want to work on a unique vehicle-based project. And that was it. There was no other information. It was a phone number. All best projects start this way. You meet in a bar, you sign a non-disclosure agreement, and you get shown a sketch of a thing that looks like nothing you've ever seen before in your life. And the guy goes to me, would you be interested in this? And I go, who wouldn't? I'm an engineer. This is an opportunity to go somewhere where nobody's ever been before. This is an attempt to take the land speed record to 1,000 miles an hour on land. The current record is 763. That was set in 1997 in Black Rock in the States by a car called Thrust SSC, driven by a wing commander of the Royal Air Force. But this project isn't actually about breaking a land speed record. This project is all about a whole other set of stories, and this is a quick video that just kind of introduces it.
We're building a 1,000-mile-an-hour car and sharing that story with a global audience. It's part supersonic jet fighter, part next-generation space rocket. Our mission is not just to go fast. It's about creating an engineering adventure to inspire a generation about the magic of science and technology and bring it to life in the most exciting way possible.
So it is a car, but it's kind of a car. And the reason this exists is because of children. This whole project has been set up to inspire a generation, to find science, technology, engineering, maths, and STEM subjects, to find those exciting and challenging. There's no point telling a 19-year-old kid that when they go to college they should study engineering because it's fantastic. Because if at age 10, 11, 12, they found math, science, technology boring, not excited, they're not going to follow that path. So this project is all about exciting children about science and using that education and using that stimulation and technology, not only to aim at school kids, but also to build up through universities, workplace, colleges, all those kind of people you can work with that actually showcase what the future holds in technology, and doing that in the most exciting way possible. Now, when you ask a kid to draw a fast car, that is not what they draw. That was the world's fastest car. And actually, the guy had thought about aerodynamics. He'd made it really good aerodynamic shape. He hadn't read the bit of the manual that says to make aerodynamics work, you need to sit inside the aerodynamics. Now, the first land speed record, the first 3 cars didn't use engines, didn't use internal combustion engines. The first 3 cars were electric, steam, and electric. That's an electric car. And it achieved a land speed record that was only slightly slower than the cycling record of the day. So that meant the guy could have started his stopwatch and cycled to the end of the track, waited for the car to come past him and click it off. But that's the start, and the beauty with land speed record is everybody uses the best of the equipment they can use. Everybody uses whatever they can get hold of. And there is huge competition, but you can share all the information. This project only works because there isn't anything you can ask me and I can't answer you. Because if I was doing NASCAR, if I was doing IRL, Formula One, all those competitive teams, they can't share everything. They hold on to IP. As an organization, we share our IP. You can download the drawings off the internet. You can see models of the car. You can build models of the car. You can try and get it there fast enough. Actually, when we put these online, the fastest set of downloads were from China, which is kind of exciting. But we've existed for the first few years of this project as a virtual project. We do everything virtually, whether that be through design or testing, all those things. There is so little you can do to physically test a car that does 1,000 miles an hour without physically building a 1,000-mile-an-hour car to test. My first experience with working with the cloud sounds really daft now. It's a steering wheel. So we're not steering wheel designers. We've got a huge problem in that the team that designed the car you see is probably between 5 and 7 people on the design team. We don't have time to do a steering wheel. So we said, well, there must be loads of people out there that want to do a steering wheel. So we scanned Andy Green's hands, the driver's hands, his grip, and we then put a competition on a system called GrabCAD. And that went global. And we had 1,300 people and organizations that were far better at designing steering wheels than we were. And they came up with all the ideas. And we said there is no limit to what you can do, but just don't make it too flexible, because on the last one he drove, he actually bent the steering wheel. So he's really keen that it doesn't bend. But if you start to look at, say, additive manufacture, there isn't any limitation to what you can't think. And we had some fantastic designs. And we ended up with a design like this one. So we printed it in nylon, got Andy to drive it. Andy got the red Sharpie pen out, scribbles out the bits he doesn't like. We start making a new one. But to see if it worked, he needs to try switches and triggers. So on that steering wheel, there are 6 buttons, and they're easy to find. Buttons are very easy. Triggers are very difficult, because triggers tend to do one thing in aircraft, and that's fire something. And they like to do that in a very different way to how we want them to work on this car. So this car, those triggers are throttles. So we set off one of the largest hybrid rockets ever been developed by triggers behind that wheel. And Andy needed to feel how they felt. So where we work in Bristol, there's a hardware store near there. So we literally went to the hardware store, and you can buy drill triggers that you get for your Bosch, your Makita, DeWalt. And so we thought, well, just for the time being, we'll put those in there and see, just to get an idea, and then we'll get some proper ones sorted. And he tries them, and he goes, these are really good. How much, wow, this is, did he get these developed? We had lots of people wanting to develop triggers for us. These were $10 parts. And Andy goes, they're the ones we want. So when we got the final steering wheel printed in titanium, the things that Andy Green launches, one of the world's largest hybrid rockets, is a $10 drill trigger. And people say, what does Bloodhound do that's different? And it's how we look at the supply chain, how we look at solving problems. How do we use what's already out there? We don't want to reinvent the wheel. We've got enough problems trying to keep a car on the ground going quite quickly. But it's how you use that and how you work with suppliers and how you find those other products out there that you could use and find acceptable. Now, some stuff is generally difficult. So we are pushing the boundaries. We are competing with some other teams, but actually the boundary we're really pushing against, our biggest competitor, is physics. We're going up Mach 1.4, 1,000 miles an hour, 1.4 times the speed of sound. We have to manage all the air around this car. If you can imagine how much energy is in a car doing 1,000 miles an hour, this weighs nearly 8 tons. Keeping that on the ground stably is a fantastic challenge. And again, we've had to use the power of computing and the power of analytical tools to allow us to work out how we can keep that car safely on the ground. Because we've got such a small team, we use techniques like topological optimization. So we optimize the product as far as we can to aim us in the right ballpark. So what we see there is the front suspension of the car. The one on the left is the model we started off with, the suspension model. The one on the right is what you do if you let a computer loose on it. You say, take away where I don't need metal. And we call that the dead goat's head because it's all kind of eaten away like a block of cheese. And if you find somebody with a really big ALM machine and a lot of money, they'd make you one of those. But actually you can't do that. So you use that as a hint and then you produce something like that. But again, working with that manufacturer, the biggest issue I have with manufacturers when I go to ask them for something is they just go, yes, we can. Then a bit later they tell you what the price is, they're going to tell you, do that for you. And you go, that's really expensive because the best price we like is the free price. But then they say, but if you'd done it this way, it'd have been a lot cheaper. But that's not what you asked for. You asked for this expensive thing. I said, well, I didn't know that you could do that one a lot cheaper. And they go, well, yeah, but nobody ever asks us. And when I've gone into the UK industry, into the UK government, the biggest thing we go about dealing with manufacturers and suppliers is ask them the question, get them to work with you, and get them to help arrive at a solution that's better for you and better for them. So it's a cheaper product, it's easier for them to make. You get far more reliability, all those good things, rather than just going, yes, of course we can do it. You can also get lulled into full sense of security with technology. So we've heard some stuff yesterday about augmented reality, virtual reality. So we build this virtual car, and you can go into a cave and you can play around with it in full virtual reality and see what you can do with it. So the engine behind there is a Eurofighter jet engine, EJ200. We need to work out if we can service it. And a company came to us and said, okay, this is really great. We can put a virtual model in a cave and you can actually try and service it in virtual reality. And I said, well, how long will that take? It'll take us about 6 weeks to get that model into the cave. It'll then take you 2 to 3 weeks, maybe a month, to work out how to use the kit, and how to get all that stuff working properly. I went, okay, so you're talking about almost 2 months to work out if I can service my jet engine. So, as I said, we work next to a hardware store. So actually, with a old desk, some cardboard, some poly pipe, and some duct tape, you can make the rear suspension of the car, you can wheel it under your gas turbine, and in 20 minutes, you can work out if the guys can service it. So there is this almost blinkered view of technology that says, just because you can, you have to. You have to always look at what is that efficiency, what are you getting from spending all that investment and time in doing it digitally, when actually everyone knows the world is held together with duct tape and cable ties. And if you can do that on a supersonic car, you can certainly do it in your workplace. This is a handmade car. This is a one-off, this is a prototype. There are no other things like this. And we use fantastic technology, we use additive manufacture, we use rapid tooling. But actually, when you're doing a one-off, actually what you really need are skilled people. We're working very closely with Jaguar, JLR. They brought their apprentices to us. So the back of the car is all titanium. It's all sheet titanium that's been hand rolled. And everyone goes, well, why didn't you use tooling? Why didn't you get some press tools done? Do you know how much it costs to do a press tool for a one-off titanium panel that's about 6 foot by 5 foot, that has double curvature on it? It is a huge amount of money. Or you find one of 5 people in the country in the UK called Gary, who is an English wheel. And Gary and his friend can actually, in about 2 days, wheel by hand a 6 foot by 6 foot sheet of titanium to a complex 3D curvature that fits perfectly. And JLR brought their design studio in and brought their graduates in and said, look, when you say you need this tooling, because to be honest, Jaguar are no different to a lot of car companies, when they do their first article, their first off body panels, they start with a billet of aluminium and they machine a billet of aluminium to the thickness of a door skin. That's great when you can do it and you can waste all that money and that time and that effort. But actually what you need are the skills that people used to have. So very strong investment with education, with apprenticeships to get those people back into use those skills to actually see what they're valued for. So we produce a car. In that car, Andy sits, and Andy goes quite quickly. He goes to 1,000 miles an hour, and in that 1,000 miles an hour, we cover 11 miles. We go 0 to 1,000 to 0 in about 95 seconds. The measured mile is 3.4 seconds long, and that is a really hard idea to get your head around about how quick a mile in 3.4 seconds is. So imagine you're sat in a stadium and you blink. Your blink reflex is a fifth of a second. Just as you close your eye, the car comes in through one side of the stadium. At the end of a normal blink, it's already gone to the other side of the stadium, and you haven't heard it coming, supersonic. You'll have heard it going, because it will have been one of the loudest man-made noises on planet Earth. We'll do 4.5 football pitches a second. To get there, we have 3 engines. We have a jet engine from Eurofighter Typhoon, so we have the most modern engine in the Royal Air Force's fleet. We have a rocket engine. We used to jokingly say we were part spaceship, part jet fighter, part racing car. We now are part spaceship. We have a rocket from Nammo in Norway. We have the largest hybrid rocket that they've developed, and that is the first stage of a satellite launch vehicle. We have a total of 20 tons of thrust. That means that if the car weighs about 8 tons and it was sat vertically, it would go up. And I got asked some questions at a school, it was actually a girls' school in Bristol, that said, well, how high does it go? I said, well, I don't know, it goes that way really, really quickly. It doesn't go up. So but it would do, you've got 55 seconds of fuel. And the physics teacher afterwards said, have you heard that before? I said, well, no, have you done some physics? And I said, yeah, we've done all that F equals ma, all that good stuff, Newton's laws. And so I sat down with them in 20 minutes using a spreadsheet. They just wrote out a little thing at time slice and said, T equals 1 plus a little bit, take off a little bit of weight, bit of thrust, bit of drag. And after about 20 minutes, they told me the car got to 25,500 feet vertically, and it broke the sound barrier at 17,000 feet going straight up. But that wasn't the number they really wanted. What the number they really wanted was, they put gravity in there. So they wanted to find out actually how hard it hit the ground as it came back down again. But the teacher at the time goes, I never understood what this project was about. I didn't see the point. I didn't understand what is Bloodhound. And he said, to get a girls' school, to get them actually finding out something that they want to find the answer out to. And for them, they were telling me, the teacher, sir, what the answer was. And it's the first time they've been in a school situation where they've told the person that's teaching them what the answer is. And they've used something they've learned at school to find out something they wanted to know. It wasn't a trolley sliding down a ramp or 2 trains crossing or anything like that. It was some stuff they wanted to find the answer out to. And that is the power of Bloodhound. This car is 136,000 horsepower. And of that, the smallest engine, a Jaguar V8, is there just to pump the fuel pump for the rocket. We've got a 600 horsepower, 5-litre supercharged V8 just to pump the fuel pump. Now, this is all virtual. This doesn't really happen in the real world. What we did this year, last year, 2017, all models are wrong and some are useful. You can analyze stuff to death, but unless you've got something to validate it against, it's completely worthless. And again, there was some stuff to talk about yesterday, it's digital transformation, about how modeling has to change, how you have to use these tools to be able to find out what's happening next. So 2017, we went to the south coast of the UK, and we started to run the car. This was an educational day. So we ran the car to something like just over 200 miles an hour, and we had 3,500 school children came to have a look at it. And with the partnership we have with Oracle and the Oracle Academy, we streamed all that data. We've got a huge relationship with Oracle at the moment about how we analyze data, how we use the tools that you were seeing yesterday and you will do over these next couple of days, how we use those to make a supersonic car work better. And here's a quick video about what it looks like. So that car did 0 to 200 miles an hour in just over 7 seconds. And that was with us lifting off the throttle at 120 miles an hour. this car's acceleration is, we had Top Gear, the guys from Top Gear were down there. They'd just done a test on a McLaren. So the new McLaren does 0 to 60 in something like 3 seconds. We did it in 3.5. It does 0 to 100 in 5 seconds. We did it in 5.1. It does 0 to 150 miles an hour in 15 seconds. We did it in 7. It does 0 to 200 miles an hour in 24 seconds. We did that in 8. And we will keep going all the way up to 1,000. But the key thing for us is the information, the data. So we stream 700 channels live off the car. And we use that data to adapt with our models. So we use the analytics tools, the machine-based learning, all those things to predict the future and look at, we can't change reality, but we can change the future. We can change those models and use the tools that Oracle provide to be able to give us the best estimates about where we go next, but also to look for health monitoring, for failures, to look for predictive health monitoring, all those things we need to do, and stream that live off the car. It is quite noisy. So the guy back there, Chris, so he's wearing earplugs and ear defenders, and it was so noisy he decided it'd be helpful to put his hands over his ear defenders. But that engine only started because of the help we're getting from Oracle. So we have a lot of interlocks on this car, and one of them said that if the engine's spinning, don't try and start it, because it's like in your own car. If it's started and you try and engage the starter motor, and bearing in mind the starter motor for a jet engine is quite big, it's a bad thing to try and do. But we were getting noise on the strain gauge. So that starter motor shaft goes around at nearly 20,000 revolutions per minute. There's some slight noise on that signal line, so it was showing it was going about 10 RPM, 10 revolutions per minute, and it was cutting out. It wouldn't let us start the engine. Had we not had the ability to stream the data to the cloud, analyze it instantaneously and see where those anomalies were, we could have spent weeks working out why this engine didn't start, because it wasn't anything that we'd thought of. And so the power of this data is phenomenal. And literally, it sounds really bad now, we hacked the code, we plugged a laptop into the cockpit, chunked out some code, and it worked, and it was fantastic. But this year coming, this is the exciting year, 2018. 2018, we take the car to South Africa. So UK on a runway, 10,000-foot runway, we could get to just over 200 miles an hour. We need more space. So we go to the Hack-Scheme Pan in Northern Cape Province. This is one of the most beautiful places on Earth. It's a dried lake bed, it's 11 miles long. We've had teams there working with us in the local community. This is what they see as their World Cup. This is completely transforming how that region thinks of itself and what it is going forward. And here's a short video that just kind of runs through what it feels like to do 1,000 miles an hour, not just the 200 you've just seen.
Bloodhound SSC, engine start. Engine winds up, NH response, NL response. The most sophisticated land speed record car in history. Bloodhound supersonic car, with the engine now winding up, ready to go. Hydraulics are starting to come up. And the generator's online. Power systems are online. The EJ200 is the most advanced military jet engine in the world. And as it winds up, and the hydraulics and the electrics come online, final checks to make sure that the car is ready to go. Temperatures are nominal, coolant's good, check your engine's ready to go. Fuel flow is good. Mission control, Bloodhound SSC, ready to run, check the track is clear. Bloodhound SSC, track clear, brakes off, rolling. stationary, engines off, hydraulics off, systems safe. Mission Control, Bloodhound SSC, safe, safe, safe.
So there are two interesting things about that video. That video is 4 minutes long. That's more than twice as long as it will take Andy to actually do that. The other thing is the speed, 1,000 miles an hour. We are going 200 miles an hour faster than the jet fighter that engine comes from. When we achieve 1,000 miles an hour, the altitude of the desert is 2,500 feet, when we achieve that, we will actually get the airspeed record as well as the land speed record, as no aircraft has ever managed to fly 1,000 miles an hour at that altitude. And we go back to the reason, children. As Paul was saying yesterday, education is key. We do not need a global load of children that want to be supersonic car designers. But we do need ones that are excited about science. And we do need a population that's literate about science and technology so they can challenge people. Do you need high-speed rail? Do you need to go to Mars? Do you need power? Do you need energy? And how are you going to find those problems out? Talking yesterday about in the next 5 years, we need to develop more than we have in the last 50 years. So when I was this age at school, which seems like a long time ago, I'm 50 in about a week's time, but in my primary school, I was taught how to use a slide rule. In the last 40 years, the world has transformed from a slide rule to a calculator, to a computer, to a spreadsheet, to artificial intelligence, to machine-based learning. These are all tools. Bill gets very excited about it's going to be the end of how we do things. It isn't, it's a tool, it's a method. When I go to schools to talk about children and engineering and science, I say, do you like being curious? Because engineering is about being curious. It's the most fantastic. I don't know what my career is going to, no idea I was going to be a supersonic car designer. The problems and the careers that these children are being built up for don't yet exist. Nobody has thought of what they are going to be doing in 20 years' time because that technology doesn't exist yet. We as a project are looking so hard for what those may be to try and showcase the future of technologies. So I'm around for the next few days, so please, if you have something that's on your horizon that you think should be on this car, come talk to me. If you think you have outreach programs that want to get to schools, come and talk to me. Now, the reason this picture is particularly special is this isn't a school in the UK. This is Hudson Elementary in Ohio. And one of our partner companies, Swagelock, was so impressed by what Bloodhound was doing in the UK, they took Bloodhound to America, and it's now being rolled out across Ohio. This is the power this project has. It isn't about a blue and orange car going quickly. It's about getting a generation excited about science to solve those problems that were so eloquently put by Paul last night. What is that future going to look like? These are the people who are going to sort out that problem. These are the people that need that energy, that enthusiasm, that curiosity to solve what the future holds for us. Thank you very much.